So I would like to say hi to everybody. During today's first part of the session, we will approach the topic of weather radar basics. First of all, I would like to apologize for not being with you at the introduction session, but I think Wilfried told you a few words about me and my activity, so I must thank him for that. Nevertheless, I would like to ask you to allow me to do a short presentation of myself. My name is Sorin Burcea. I'm working at the Romanian National Meteorological Administration since 2004. My position is a research scientist, but together with my group, we are doing operational and research activities. The operational activities consist of, first of all, in the coordination of the National Weather Radar Network. And the research activities are mainly based on the study and research of severe storms and climatology of the associated weather phenomena, of course, mainly using the weather radar data. As you all know, as meteorologists, because I was also working as weather forecasting for a short period of time, it is very important to have knowledge on how the weather radar works, and most important, how the data are sampled by these systems so we can correctly interpret those. So that being said, what you can see here is the outline of the short talk. So we will have a small introduction. After that, we will talk very briefly about the weather radar systems and the basic principles of the scanning. I will introduce you some few very basic things or issues about the Doppler and the dual polarization. Following that to be talked in much more detail during the next session. So Wilfried and Martin will tell you a lot more on the Doppler, what you can do with the weather radar using the Doppler effect and also the dual polarization. So actually, what radar means? I think all of us knows what radar means. It means that we can, given a target, we can send radio waves, and through the propagation of these, we can detect that and we can calculate a range to that target. In our case, it is about the meteorological targets, so the precipitation particles, but also during the following lessons, we will see that the radar does not see only the precipitation, but also another targets. So the first question which came into our mind is who invented radar? To my knowledge, it is not a single person that it is attributed with inventing this system. It is a collaborative effort. So starting with the, let's say so, the discovery of the electromagnetic waves and the effects, most of the or some of the researchers have studied the use of these and applied to the radars. The radar was first used in the military, if I'm not wrong. So a significant development of the radar techniques were developed during the World War II, when they were trying to see the enemy aircraft, but they also they have also seen something on their displays that actually it was quite annoying. So they realized that were actually the clouds, the precipitation clouds. So after that, the technology evolved. Radars, especially built for meteorology, were developed to the national weather services, and nowadays they are widely used, and they are a very important instrument in the in our work, yeah, as a weather forecasters. So, like I said, the importance of radars is that they are used in nowcasting, which is the very short weather forecasting. For example, here in Romania, we have this division in the national forecasting centers, where weather forecasters are concentrated only on watching, on detecting and watching the evolution of a storm, so they can issue warnings in case severe weather occurs. They are also used in hydrology, yeah, because the weather radars can estimate the amount of rain that falls to the ground, and they are also very useful in severe weather detection and also for aviation. Talking about evolution, what you can see on this display on the left is a radar display, um, and how it was looking in the 1960s. You can see here some shapes, yeah, which are coming actually the echoes from precipitating clouds, and you can see on the right the advance in technology, in processing and software, and visualizing. And this is a volumetric radar display which can be showed, for example, can be obtained using the newest software development. So you can see how the evolution was going. Also, the technology is evolving very fast. Um, they are trying new ways to improve the weather radars. So now I think they are testing the so-called phased array radars. They are not yet deployed, yeah, like for operational, but they are in research. They are doing research on that. Um, so why do we need to use the weather radars for forecasting? First of all, because it is a vital tool. Why? Because it has the advantage of high spatial and temporal resolution. If we are comparing with the classic rain gauges, which they are used to measure, for example, the amount of rain, to measure the, let's say, the wind speed, the amount of snow or something, we can very quickly see the difference. We know that the weather phenomena has a very large spatial and temporal variability. So using just one measurement system, it's not so relevant. So we need to find all the time more ways to have a better coverage of the weather phenomena. So the weather radars have this advantage of very high spatial and temporal resolution, and it shows us where the rain is, for example, and how intense the areas of precipitation are. Also, it shows us where the weather systems are in near real time. Why? Because the scanning frequency of the radars now are, let's say, in the order of few minutes. For example, in Romania, we have a time between scans of a time between every volume scan of 6 minutes. So every 6 minutes you have new information on where the weather systems are. So it is a very powerful tool to detect the severe thunderstorms. We can also monitor their movements. We can also detect the fronts, for example. So this makes the weather radar a crucial part of the weather forecasting and especially of the nowcasting systems. Talking about severe weather, we all know that the severe convective storms are the most damaging, and they are those that they are threatening our lives and also have high or very high socio-economical impact. Usually, these severe convective storms are associated with large hail, with strong winds, with heavy rainfall, with lightnings, from which the most dangerous are the cloud-to-ground lightnings, or they can have a combination of two or more of these weather phenomena. So it is very important to have a weather radar to cover an area of and to be able to make a very good forecast. From the point of view of the remote sensing, the weather radars are cataloged as active remote sensing systems because comparing to with the passive ones like radiometers or the weather satellites, the weather radars they can generate electromagnetic energy transmitted into the atmosphere and receive it back. So that's why they are called active remote sensing. Not like the satellites, which are just, for example, receiving the radiation from the clouds. They do not have an emitter. Yeah, they cannot generate electromagnetic radiation and emit it to the atmosphere. From the point of view of the electromagnetic spectrum, the electromagnetic radiation that it is used by the weather radars falls into the microwaves spectrum. So the wavelength can vary from 1, let's say, or 3 to 10 centimeters. It is known that in radar meteorology, we are using systems that they have a wavelength of 3 centimeters, which they are called X-band systems. Those that they are characterized by 5 centimeters wavelength, they are called the C-band weather radar systems, and the S-band, they have a wavelength of the electromagnetic radiation of 10 centimeters. So that being said, let's go further and talk a little bit and very briefly about the how a radar system is built. Actually, it consists of few main parts. One of these is the transmitter, which actually takes the electromagnetic energy which is generated by a magnetron or a klystron, and then it is sent through the antenna and follow it to be sent into the atmosphere. When the energy came back to the antenna, we have the receiver, which receives the electromagnetic energy, and it is passed through the processor, and after that it is sent to the data processing and display. So the main components of the radar system are the transmitter, the receiver, the antenna, and the data processing and display. When we are talking about the antenna, we should consider more than just the parabolic reflector that it is used to focus the electromagnetic energy into the atmosphere. What you can see here in this picture is actually the whole ensemble of the antenna, which is composed also by the pedestal, the radome, and some part of the waveguide, the rotary joints, and everything. So actually, all this part of the system is called the antenna. Further, when we are talking about basic principle of the weather radars, we can talk about how the radar sends and receives the electromagnetic energy into the atmosphere. So we have the radar here. Let's make the assumption that this is a weather radar. We have the transmitter, and through the antenna, a electromagnetic pulse is sent into the atmosphere where it reaches a target. When this, after this energy is transmitted and reaches the target, some of the energy, a very small part of that, is back scattered to the antenna, received, processed, and after that we can through the display systems, we can observe, we can see the information that comes from the targets in the atmosphere. So very shortly, this is the principle. We need to take into account that when we are doing measurements with the weather radar, we don't have just a single target, but the targets are distributed in the atmosphere, and we will see later how this contribute to the backscatter signal at the radar. So let's say that in general, the weather radar transmits very short pulses of radiation or electromagnetic radiation. These are organized into a pencil beam, yeah. So it is called the radar beam, which is very narrow, yeah. This pencil beam, this radar beam expands outward, also horizontally and vertically. So at greater distances from the radar, its dimensions are getting bigger. Very short at the level of microseconds. The transmitted power is very high at the order of kilowatts or megawatts. It depends. And after that, the radar listens for the return energy, so we can have those echoes that we can very nicely see on our displays. So, as I said earlier, these returns are very weak, so they need to be amplified and processed until they are displayed. Yeah. So after transmitting the energy into the atmosphere, we can see the precipitation. We can have targets that they are on the ground. We can see the terrain. We can see insects, birds, and so on. These are just a few examples of what the radar can see. You can see here on the left the echoes coming from the ground targets. We can see, of course, the clouds, which is what we are interested in. We can see the insects. We can see the smoke. But these are part of another session that we have in a few weeks, which regards the non-meteorological targets, and we will see how we can interpret those. Given a target, we need three pieces of information to determine the exact location. And those three pieces are the azimuth angle, the elevation angle, and the distance to the target, which is called the range or the slant range. So if we have the radar, we can see here on the upper left-hand side a top view. So for example, if we have the north arrow, one of the angles is the so-called azimuth angle. So the azimuth angle is the angle between the north direction and the direction where the antenna is oriented. The elevation angle is the angle between the horizontal and the angle at which the antenna looks high up into the atmosphere. Having this and the distance to the target, we can exactly estimate how far, for example, how far and how high the target is related to the radar. Of course, the minimum distance that can be determined is given by this relation here. So it is CT to the 2, yeah, because the pulse needs time to reach the target and return back to the radar. We introduced earlier the radar beam. So when the radar emits the electromagnetic pulse, we can it is illustrated here how this radar beam spreads as we go further from the radar. You can see here the pulse length, and a very interesting thing which need to be considered here is the so-called pulse volume. Because, for example, in this volume, The radar takes information from all the targets that they are within this volume, and the information from here, it is what you are seeing in the radar pixel on the display. If you are looking on at the side view at the radar beam, we can see the beam center line, which is the area where the maximum power of the EM energy is, and we see also the half power points, or the so-called beam edges. So this is what defines us the radar beam. So this radar beam propagates into the atmosphere like this, like how it is illustrated here. You can see the trajectory. This could be, for example, in the case of standard diffraction. So this would be in the standard atmosphere. But for example, if the atmospheric conditions are changing, the beam propagation differ from the normal one. So we can have, for example, subrefraction, where the beam is getting higher than the normal, the trajectory is higher than the normal one. And we can have also the superrefraction, when the beam is propagating lower than the normal propagating conditions. These are also a few illustrations. I think I will go very briefly on that. So in the case of the subrefraction, you can see here that the main beam is propagating higher. So we can, for example, the beam can overshoot the clouds and we will have no information on the radar. We can have also the superrefraction, where the beam is propagating on a lower altitude than the normal one. And we can have this case where it's a extreme superrefraction case, which is called ducting, where the beam can propagate and can also hit the ground at some distance from the radar. So we need to be aware that the radar measurements have also some limitations. Some of these, they can be ground clutter, they can be anomalous propagation, which is actually what was in the previous slide. We can have partial beam filling, so actually the beam is propagating into the atmosphere, and it is not sampling only the precipitation. So it's, let's say that the pulse volume is full just half of the target. We can have weather dome, or we can have incorrect hardware calibration, which needs to be fixed immediately. So in that way, we can have the most correct information. It is very important to have in mind that the radar beam is propagating like this. If we have the Earth, we can see also here the curvature. We need to be aware that at very long distances from the radar, the measurements are performed very high in the atmosphere. So as we are getting away from the radar, our measurements is performed higher in the atmosphere. You have here illustrated also a diagram, which is the distance versus height diagram. So if we consider the Earth as flat, and we have the radar here in the origin, you can see that at different elevation angles, as you go further from the radar, the altitude at which the measurements are performed is getting higher. So we talked about earlier about the elevation angle and the azimuth angle, and using this, the radar is performing a volume scan. It means that the antenna is rotating 360 degrees in azimuth at different elevation angles. This is done in a certain time interval, and you would have the information which consists of a volume scan. So if you see here the beams at different elevation angles, it rotates to 360 degrees, and you have this volume scan, where actually you have three-dimensional information on the weather systems in the coverage area. Be aware of the cone of silence, because here right over the location where the radar is installed, you would have no information. So after the radar is performing the volume scan, the data are processed and they are sent to the display stations, so workstation. So when you see an image like this, you need to know what kind of a display is that. For example, here it is illustrated a plant position indicator, which actually consists of the projection of the data from one elevation angle. So you have here in the upper right side, you have a scan at one single elevation. So you have this cone, right? So if you are looking from the top, you are projecting this in plane. You will see this image. You will see this image here with these very nice echoes. Another way of displaying the radar information is the so-called CAPPI, which means it's an acronym of the Constant Altitude Plant Position Indicator, and it means that the radar algorithm is taking the measurements at a constant altitude. So from all the elevation angles available in a volume scan, the radar or the algorithm chooses just those ones at the, uh, those ones where the radar beam intersects the clouds at a certain level. For example, here you can see illustrated that a CAPPI would be, for example, at 4 kilometers, and here, for example, at 1.5 kilometers. In this picture, you see a CAPPI image of the reflectivity. Disadvantage, let's say, of this display would be that you would have these circles that they are very well distinguished, right? So you can distinguish very well these circles. So you would not have a very continuous field of values. Why? Because we saw earlier the radar takes the information available at a certain height. Another way of displaying radar data is through the range height indicator, which is actually a cross section. Yeah, so it's a vertical cross section through the clouds. So, for example, if you are, of course, some of the weather radar system can do this also technically. So you can actually align the antenna on a certain azimuth, and after that, the antenna is moving indicators using the volume scan data. So, for example, if you are doing a cross section, let's say I have here an image on the right side, you can see this very intense echo here. And if you are doing a cross section, here you would have this display on the left. So, for example, between 120 and 180 or 200 kilometers, you would have information, and you can see where that information and how the values are distributing over the vertical. Yeah, so you can also assess the height. So let's say you have very big values at the height of let's say 8 kilometers. When we are talking about single polarization radars, there are three types of information that it is used. One is reflectivity, which will be introduced to you in the second part of the presentation by Martin Hagen. You have the radial velocity, and you can interpret that using the Doppler effect. I think Wilfried will talk about that in a coming session. And you have also the spectrum width, which is also related with the distribution of the velocities inside um, the pulse volume. So actually, this information can be very well used in detecting, monitoring, and forecasting the evolution of the thunderstorms. Of course, with the new technology, you can of dual polarization, you can have more information, and the outcomes and also the automated products, they are much better than in the case of single polarization weather radars. So talking about the radial velocity, right? You can have information on how the severe convective storms or the storms are organized, because you can have information on the rotation inside storms. You can have information on how they are moving, what is their trajectory, and so on. So the Doppler radar actually it uses the Doppler effect, which means that it measures the return power and also the phase shift between two consecutive pulses. Yeah, so we know that the objects moving towards the antenna, they have a larger frequencies. Yeah, then the wave frequency is bigger than in the case of the objects that they are moving away from the antenna. In our case, the precipitating clouds. What is very important to know when you are interpreting the velocity images is that that's why it's called also the radial velocity, because the it represents the projection of the actual wind component along a radial. So it is not always what you can see along a radial. It is not always very accurate. Why? Because it depends on the angle between the actual component and the azimuth. So you have here the table, yeah, where you can see that, for example, at 90 degrees, if a target is moving at 90 degrees related to a radial, the estimated speed is 0. And for example, if it's moving on the 0 or 180 degrees, you would have that the radar measurement is the most accurate. So we need to be aware of that. As I said earlier, the technology is evolving. Now, the dual polarization radars are used by more and more weather services. A lot more information on the observed targets. So with the dual-pol measurements, for example, those three base moments are supplemented by another ones, which are, for example, on the observed targets. So with the dual-pol measurements, for example, those three base moments are supplemented by another ones, which are, for example, the differential reflectivity, which is a good indicator of a drop shape, and we can also estimate the average drop size using this parameter. You can use the correlation coefficient, which can give you an information about the mixture of precipitation type, and it is very good at discriminating the non-meteorological from the hydrometeorological targets. And you can have also another parameters that they are, for example, they are very good in estimating the rain rate and following also the rainfall accumulation. So I would like to give you a summary. We didn't have too much time to talk about this. I was trying to offer you the very basics and very simple information that you can retain when you are seeing a radar image and how you can interpret that. So the weather radars, that has varied uses. It is used, of course, first for detecting where the precipitation and how intense it is. It is very useful for short-term weather forecasting. And if you are doing in your Met service, you are issuing warnings, you would see that the weather radar is very helpful in that situations. It has use in hydrological applications because you can have automated algorithms that can estimate the amount of precipitation, and after that it can be feed it further into hydrological models, for example. And of course, it can be used also for other things, like, for example, tracking bird migration patterns. Yeah. So That being said, uh, I want to thank you, and I want to say that we also must be aware of the radar's limitations. So you would see through the following sessions that it is very important to know how to interpret the information. So I hope that you received the very basics on how the weather radar functions and how the data are sampled, and we the microphone to Martin for you to have a continuation of this session. Thank you again.